Great. My name is Mr. Jackson.
And my name is Miss Hughes.
And we are about to begin Unit 3 and the Introduction to Probability.
Yeah.
And this is probably, this is probability, the best unit in the course. This is probably one of my favorite units in the entire course because it really represents the culmination of kind of everything that we've talked about in permutations, combinations, and it really gives a nice context.
Yeah, I agree.
So first of all, what is probability?
Okay, so it's the branch of mathematics that attempts to make predictions to answers in questions about likelihood of things happening or occurring, right? So probability is our way of trying to predict the future. And so we use our counting principles. We've spent all this time learning permutations and combinations. And if we want to know what's the probability that so-and-so will finish the race first, well, so far we've just been finding in how many ways could that person finish the race first. And now we're actually going to take that and put it over a denominator and turn that into a probability. So we're going to turn those numbers, how many just counting, into something that we can now use to make predictions. Okay, so that's the whole purpose of probability.
Yeah. And so really what we're talking about is we're talking about events, right? And so one thing that we're going to talk about a lot is the probability of a certain event happening, right? Or the likelihood that that event will occur. Well, an event is basically a collection of outcomes that satisfy a particular condition. So that condition may be given in an example or it may be given in a problem. And so we want to find the number of ways that that event can happen. So an event is basically the collection of these outcomes. The probability of any event can range from 0, which would be an impossible situation, to 1, which would be a certain situation. So a probability of 0 means that this event will not happen, and a probability of 1 means that this event is certain to happen. Probabilities that have less than 0 or greater than 1, they have no meaning.
Yeah, and this is helpful to you in solving problems in that if you're using methods to find probabilities and you get like negative 20% or 1.5 probability, then you may have done something wrong.
Yeah,
because
exactly.
any probabilities that are less than 0 or greater than 1 have no meaning. You can't be more certain than 100% certain.
Yeah.
Right.
So if you say, the probability of this happening is 150%, that really mathematically has absolutely no meaning whatsoever.
No. And if you get 150% for your answer, then you got to go back and recheck.
Yeah. So a little bit of a notation, suggestion for notation is the probability of some event E is noted as capital P, and then in brackets we would write the event, right? So it's a measure of the likelihood that event will occur. Probability can be expressed as a fraction, a decimal, or a percent. So we could say 1/2, the probability is 1/2. We could say the probability is 0.5, or we could say the probability is 50%.
Yeah. If you want to keep exact values, then I would recommend keeping it as a fraction, because then you avoid the approximations of rounding in decimals and percents. You'll see your textbook does both. Note the contrast here. When we write P of E, or the probability of E, it should remind you of what we were doing numerically. We would say the number of ways E can happen.
Yes.
Versus the probability that E will happen. And in fact, the number of ways E can happen is one of the calculations to find the probability that E can happen.
Yeah. So there's 3 basic types of probability, and we'll talk about the first one here, the empirical probability, or as we call it, the experimental probability. And we've got a definition. And basically, the experimental probability of a particular event is calculated in an experiment, so in a probability experiment. And we divide the number of times that the event actually occurs by the total number of trials that we do. So here's a very, very simple example, and to complete this example you'll need to find a dice. So hopefully you have a dice somewhere that, as you're watching this, you can go and grab. If you don't, no problem. You can just imagine right along with us.
Yeah, you can even run a simulation. If you tear a sheet of paper into 6 small pieces and write the numbers 1 to 6, and toss it into a bowl, then whatever you pull out, that would simulate rolling a 6-sided die.
So basically you roll the 6, and basically what's going to happen is that let's find the experimental probability of rolling a 1. And so if we were to roll this dice 6 times, right? We're going to roll it 6 times. We could get maybe 0 6s, maybe 0 1s, maybe we get 1 1, maybe we get 2 1s. Hey, if we're really, really on a roll, maybe we get 3 4 5 1s. But of course, the number of times that we're going to get 1 is going to happen more often than not. And so if you do this little experiment a number of times, you'll find that sometimes you'll get 0 ones, sometimes you'll get 1 1,
Yeah.
sometimes you'll get 2 ones, but most of the time you're going to find 1 1.
Yeah, and that's because the probability of rolling a 1, there are 6 outcomes on the face of your die, and only one of them is the number 1. So really, for every 6 rolls, you should get a 1, you know, on average. And so that's sort of, when we do the experimental probability, you find that you start thinking about theoretical probability to get there. We'll talk about that in a second.
Okay. And so basically, if you want to do this, go and grab yourself a dice, and you can do this little experiment. You could probably also find a web applet of a dice being rolled that you could do. So basically, what you'd find is, hey, instead of rolling the dice 6 times, now, I don't know, try the same experiment. Roll the dice 60 times.
Yeah.
Now roll the dice 600 times. And what you'll find is that, of course, the theoretical probability of rolling a 1 is 1 in 6. Because you got 1 shot out of 6 total outcomes. So you'd have a 1 in 6 probability. And as that number of trials gets closer and closer and closer to infinity, right? So as you go to from 6 trials to then maybe you're going to go to 60, and then you're going to go to 600, and then maybe you're going to go to 6,000, then you're going to go to 60,000. If you did this for 60,000 trials, pretty much what you're going to find is that your experimental probability is getting pretty close to what theory tells us. And this is an important little distinction, that any experiment replicated an infinite number of times is going to give us a theoretical probability.
And you can sort of think about that rolling an infinite number of times or having an infinite number of trials is kind of similar to a population. You know, and the larger your sample is, then the more it approximates your population. Well, the larger your sample size here is, the larger the number of trials, the closer it's going to approximate the theoretical probability, that bigger concept.
And so really, the basis of this unit, most of what this unit is all about is calculating theoretical probabilities. So here's a good definition. The theoretical probability of a particular event E is deduced from analysis of the possible outcomes, assuming that all outcomes are equally likely to occur. So we're not talking about loaded coins or loaded dice. We're talking about fair coins, fair dice. It's calculated by dividing the number of desirable outcomes by the total number of outcomes in the sample space. So here we define the theoretical probability as the probability of some event, which is equal to the number of ways that that event can happen, divided by the number of ways that any outcome could happen. That basically the number of outcomes in the sample space, which is n sub s.
And what you'll, a good way to think about this is that in the previous 2 units, you were often given a scenario, and then part A was find the number of ways without any restrictions. And then part B was find the number of ways with Alphonse being first in line. And so then we start to build part B, C, and D have the restrictions. What you'll notice here is that when you're finding the theoretical probability of an event, that sample space, that denominator, is the no restrictions, all possible ways, no holds barred, put everything in a pile and pull out 5 of them, like whatever it is. And the numerator would be like the part B or part C or part D sitting there on top of that fraction. Okay.
So here, calculate the theoretical probability of rolling a 1 on a 6-sided dice. And we've already alluded to the answer, and you should have some idea about what the answer is going to be. Well, if E is the event of rolling a 1, then our sample space, well, what's the total number of outcomes on a dice? Well, it could be a 1, a 2, a 3, a 4, a 5, or a 6. And so then the number of ways that we can roll a 1 is just 1. There's only one way. If you roll a dice, there's only one way that you're going to get a 1.
There's only one on there.
The total number of ways that we could roll a number is 6. And so then the probability of rolling a 1 is simply 1 in 6. Okay? So another interesting thing to note is, okay, well, let's say we took the sum of all the probabilities, like so the sum of all possible
So
events.
probability of rolling a 2 is also 1 over 6. Probability of rolling a 3 is also 1 over 6. Each probability in this case is equal. It's a uniform probability.
Yep.
And so if you took your 1/6 plus 1/6 plus 1/6 plus 1/6, you can only roll a 1, 2, 3, 4, 5, or 6. And what's neat is that if you've considered all the possible events and all the possible outcomes, then if you add all those probabilities together, they'll always total 1 because something has to happen.
Yeah. So when you roll a dice, the probability that you roll something is a 1.
Yeah.
Because a dice is not going to end, it's not going to land on an edge,
Yeah.
or it's not going to land on a corner.
Yeah.
The probability that something will be face up is 100%.
Yeah.
So 1. All right. So now let's talk about, this is the most fun one, the subjective probability.
This one's crazy.
And a subjective probability is an estimate of the likelihood of an event based on intuition and experience. So it's an educated the guess. So the probability that I will sleep in tomorrow and I will miss my first period data management class is likely 0.00002%.
Yeah. Because have you ever done that before?
No. I haven't. I actually haven't in 5 years, touch wood.
Yeah.
In 5 years I haven't slept in and missed first period.
Yeah. So you're estimating, based on your history, based on your intuition and your experience, you're estimating an extremely low probability of you sleeping in and missing your Block A class tomorrow.
So, Ms. Hughes, maybe you can do this one. Estimate the probability that the next pair of shoes you buy will be the same size as the last pair you bought.
Okay, so, and this is different for everybody because it depends on your feet and how you shop. I know some people, it's a different pair of shoes almost every time they go.
Yeah, different size, yeah.
For me, it's always been a size 7, always has been, always will be. And so I could say that, my subjective probability is probably way up there. Like maybe if I go and buy Birkenstock, something is different.
Yeah.
But I'm probably up like 90, 95% probability that, that my shoe size that I've always had when I go to buy my next pair of shoes will be the same. And that's just based on my intuition and experience. What's neat here is that, we can't really give you a test question asking you for this and then give you a mark.
No, because it would be totally different, yeah.
But we could give you a multiple choice question that says, if I estimated the probability the next shoes I buy will be the same size as the last pair I bought, using intuition and experience, what kind of probability is that? A, subjective, B, empirical, C, theoretical.
Yeah.
Like you can understand the concept without us actually having you provide us a numerical answer here. Okay. People use this kind of probability all the time in their day-to-day lives.
Yeah.
Okay.
And like the probability of our, of our KCI Raiders rugby team, winning a game, is a subjective probability based on how we've done this season, based on who we're playing and how they've done this season. We could say that the probability would be, well, it could be the same as this. It could be 95%. Right? But of course it's subjective, and of course that would change. It could range anywhere from 95% all the way up to 100.
Yeah. So just bear in mind that most of your experiences in this unit will be with theoretical probability. You'll start to do some experimental probability when you create your own game. And then the subjective probability is just a concept we want you to kind of keep in the back of your mind.
Okay, so let's talk about the complement of an event, because this is an important characteristic and it plays into the fact that the sum of all probabilities is 1.
Is 1, yeah.
Okay.
Yeah.
So the complement of an event E is written as E prime or not E. Okay, so E prime is usually what we'd say.
That's what I would say, yeah.
E prime is the event where E does not occur.
So if you were to say, like, if we defined E as the event of rolling a 1 on a 6-sided die, then E prime would be not rolling a 1, which would be 2, 3, 4, 5, and 6.
Yeah.
So then the probability of getting E is 1 over 6. The probability of getting E prime is 5 over 6. And you know that the 1 over 6 plus the 5 over 6 is going to get you 1.
Equal 1.
And you can visualize this as a Venn diagram where you just have one little set, and that's set E.
Yeah.
And then everything that's not that is E prime.
Yeah.
And that whole box, that's the sample space.
Yeah.
Right? So that would be like your universal set.
Well, what's nice about this is that we can actually use this in calculations, because sometimes if it's quite difficult to calculate E prime on its own, say we'd have multiple cases and stuff like that, we can sometimes use an indirect method with probabilities as well. And you'd be familiar with an indirect method. We could say, okay, well, the probability of E prime then is just 1 minus the probability of E.
Yeah.
Okay? So let's take a look at an example. What is the probability that a randomly drawn integer between 1 and 40 is not a perfect square?
Right? So a perfect square is when you take the number and square it.
Yeah.
Right? And there are definitely more numbers that are not perfect squares than there are
Yeah.
numbers that are perfect squares.
Yeah.
So there are more desirable cases than undesirable cases.
Yeah.
And usually when that's the case, you want to pick an indirect method.
Yeah.
So we're going to sort of show you how to work that through.
All right, so E is the event that the number is a perfect square. What perfect squares exist between 1 and 40? Well, 1, because 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. So these are the perfect squares between 1 and 40.
Yeah.
All right? And so the number of ways that a randomly drawn integer between 1 and 40 is a perfect square. The number of ways that the number is a perfect square is 6, because there's 6 of these. Right? Well, basically, the number in our sample set is simply 40, because there's 40 numbers that we could draw out
between 1 and 40.
Between 1 and 40.
Yeah.
So the probability then that a number is a perfect square is 6 in 40. Okay?
But we want the number that
probability
that it's not a perfect
Yeah,
square.
so let's use an indirect method. We can say, okay, the probability of not a perfect square is equal to 1 minus the probability of a perfect square, and we get 1 minus 6 over 40. And if we simplify this, we get 34 over 40.
Yep.
So here's another one. Determine the probability of rolling a sum of 7 with a pair of dice.
Okay.
All right.
Now this type of problem, whenever you're rolling a pair of dice, it's going to be much easier for you to use a method where you make a 6x6 grid. Okay.
Yep.
Because we want to know how many ways can we roll a 7. If we start thinking about it, like, okay, well, you could roll a 1 and a 6.
Yeah.
You could roll a 3 and a 4. You could roll a 5 and a 2.
Yeah.
But then the question is 5 and 2 different than 2 and 5? Because you have two different dice.
Yeah.
And then is 1 and 6 different than a 6 and a 1? And is 5 and a 2 different than a 2 and a 5?
And we would say yes, it is.
We would say yes, because the two dice are in different positions on the table. You know, they could be different colors. Like, you know, we can tell the difference between them. They're distinguishable. So there are different ways that it can happen. And you can sit down and brainstorm them all and hope you didn't miss any, right? And here it looks as though that we've got 6 ways that we could roll a sum of 7 with a pair of dice.
And so the number of ways of this event happening is 6.
Yep.
All right, so now the question becomes, okay, so what's NS? What's the total number of outcomes that we could have when you roll a pair of dice?
Yeah.
And so you say, okay, well, let's introduce this mechanism, a 6x6 chart, for representing the sum on 2 dice.
Yeah.
Now this looks very similar to a multiplication table, but it's not a multiplication table. Here we don't have 1 times 1. It's a sum table.
Yeah.
So we have 2. We get 2 times 1, or sorry, excuse me, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7.
And what these represent, that line across the top is your first die,
Yeah.
and then the vertical line going down to the left is your second die, and so they're distinguishable. So then you're like, well, it could be a 1 and a 2 or a 2 and a 1, and those are 2 different 3s. Right? Yeah. And so if we actually want to, we can just look and we can see, oh, how many 7s are there? 1, 2,
there
3,
they are.
4. There are 6 7s, just like we, sort of put that together logically. But once you make this 6x6 chart, when you're rolling a pair of dice, you can see all the outcomes are on there. If we want to know what's the probability of rolling a sum of 5, well, then we can see that there's 4 of them.
Yeah, we can say, hey, what's the probability of rolling a 10? There's 3 of them.
Yeah.
And so basically we can go from here and we can say, okay, so how many total outcomes are possible? Well, this chart, a 6x6 chart, represents the total number of outcomes that you could get. And as we see, there's 36 of them. So the number of ways, the number of outcomes of rolling 2 dice is 36. There's 36 possible outcomes. And so the probability then of rolling a 7 is 6 in 36, which is 1/6. So out of 2 dice, 7 is the most probable outcome. It's one of the reasons why in a lot of dice games, 7 is either a number that you would gamble on or a number that you would not gamble on. And not really saying anything about gambling money, but because it has the most number of outcomes, it's one thing that you would say, oh, it's got the highest probability. The probability of rolling a 7 is higher than the probability of rolling anything else.
Yeah, absolutely.
So here's an example where, again, we're going to start to use some counting principles. And the next lesson, lesson 2, will be heavily devoted to counting principles. But because tree diagrams are really the way that we've introduced a lot of organized counting, let's use a tree diagram to illustrate flipping 3 coins.
Yeah.
And then we'll determine the probability of getting 3 heads in a row. And then we'll determine the probability of getting at least 1 tail. But we'll use the tree diagram to do
help us
this.
do this. So imagine if you're going to flip the coin 3 times, you're going to flip 3 different coins. Either way, there's 3 stages. There's the flip 1 stage, there's the flip 2 stage, there's the flip 3 stage.
Mm-hmm.
And when you go to the flip 1 stage, you say, all right, well, it could be heads or tails, right?
Mm-hmm.
And now we're just deciding on different paths. Well, if it was heads, then in flip 2 could be heads and tails. If it was tails, then in flip 2 could be heads and tails, and so on. And now in flip 3, we're going to build and build and build. Now what we're going to do here that we hadn't done before is we're going to create a separate column out to the right called outcomes. And we're going to put them in order. So if you follow along, you're going to have heads, heads, heads is the first outcome, and then heads, heads, tails is the second outcome, and then heads, tails, heads, and then heads, tails, tails. And then tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. Okay, so you can see how there's one outcome that's all heads, one outcome that's all tails, and then all kinds of combinations in between, right?
So there's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes when you flip 3 coins.
Yeah, which was 2 times 2 times 2. Those 3 stages, 2 choices each stage. We know that would be 8 anyway. So we know the sample space is the total number of outcomes. This is all that can happen. So we know that the number in the sample space is 8. And then if we want to know the probability of getting 3 heads, the probability of getting head, 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 well, we notice that there's only one way
that can happen
out of the 8. So that's just going to be 1 out of 8.
Yeah. Okay.
So
there it is. So 8 possible outcomes. And the probability of getting heads, 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 as we said, is 1 in 8 possible outcomes. The probability of getting at least 1 tail means that really we can have 1 tails, 2 tails, or we can have 3 tails. The only thing that we don't want is the case where we've got heads, heads, heads.
Yeah.
So in this case, it's probably good to use the complement or an indirect method, and we can say, hey, the probability of getting at least 1 tails is 1, minus the probability when we have all heads.
No tails, yeah. Because no tails is the only undesirable case.
Exactly.
Yeah.
And so that gives us 7 out of 8. So the probability of getting at least 1 tail in 3 flips of the coin is 7/8.
Yeah.